Stokes theorem. Stokes theorem. All that the Stokes theorem is saying is that if you have a line integral over a closed curve, if you're evaluating a line integral over a closed curve, you can simply convert that line integral into a double integral and evaluate. So double integral over, let's say, q, then curl f, curl of the vector dot the normal vector. Yes, good. Where q is our new domain. So now this one is on C. So let's try an example over here. We are going to try and see how these two values give us this, or evaluate to the same value. These two expressions will evaluate to the same value. So first of all, we are going to use this example. So use Stokes theorem to evaluate this expression. So what we are going to do is that we evaluate this and we evaluate this separately. So when you ask a question of this sort, you can either use this or use, depending on the complexity of the evaluation. Good, but most of the time this is easier to do. So let's take this and do first. But we need to sketch the region of integration. So this our x, and this is our y, and this is our z plane. Good. So this is our intersection. So at this point we have 1, 0, 0. Then we have also 0, 0, 1, 1, 0, 1, 0. Then we also have 0, 0, 1 over here. So now that we have finished plotting our region, we can connect them. So this will go here, this will connect to this, and this will also connect to this. So now this is our surface that we are going to evaluate. This is a surface integral. So we are going to evaluate this surface integral over this bounded region with a positive or with a counterclockwise orientation. So it means we are evaluating in a counterclockwise direction, and our normal vector is pointing upwards. Good, it's pointing upwards. So this is our normal vector. It's a vector. Good. Now, Stokes theorem is saying that this is the same as evaluating along this line, and this. So we could also have C1, then C2, then also we could also have C3 over here. So we are going to do the right hand side, we are going to do the left hand side and the right hand side, and see how they are equal. Now let's find our curl f. So our curl f is equal to, we have I, J, K. Then we have the del x, and we have del y, Then we also have del z. Now our vector or our function is, we have the vector field given to us is z squared. Then we also have y squared. Then we also have x. Good. So now let's try to find the curl of this, or let's try to evaluate this. Now this will be equal to this will give us del del y of x 0, del del z of y squared 0. So we have 0i, these are vectors, then minus into bracket this and this will give us del del x of x, which is 1, minus del del z of z squared, which will give us 2z. Then we have our j. Then this will give us 0, 0, so plus 0k. So our curl f is 2z minus 1, 2z minus 1, that is j. Now we need to find our normal vector, which is n. So to do that, we need to find the equation of the whole system, the equation of the whole region over here. So we know that the equation connecting these two lines is x plus y is equal to 1. Then with this one we're going to get x plus z, we're going to get z plus y is equal to 1. Then here you're going to get z plus x is equal to 1. So it means the whole equation is given by x plus y plus z, x plus y plus z is equal to 1. So to find a normal vector, we can express everything in terms of z or y or x. I prefer express everything in terms of x, y. So z equal 1 minus x minus y. Good. Now our zx will be equal to -1. Then our zy will be equal to -1. So now our normal vector is equal to zxi as minus negative zxi and minus zyj and zyj minus plus k. Oriented upward, so this is supposed to be positive, and the positive orientation is on the k. Good. Now if this is our normal vector, we just substitute this and this. So you are going to get I plus j plus k. So this is our normal vector. Now our unit normal vector will be over the square root of this square. It is 1 square plus this plus that. But we are going to substitute this into this formula. The ds also have that in it, so it's going to cancel out. So what we are actually going to substitute is just this. We are just actually going to substitute this into our formula. So there's no need to work for the unit normal vector. Normal vector will suffice. So now we have our curl f dot. So let's dot the curl f and this. So our this expression now will be equal to this double integral over, let's say, d over d, then cal f dot n ds is now equal to dotting these two vectors. So we have 2z minus 1, 2z minus 1, 2z minus 1 j, 2z minus 1 j dot I plus j plus k. So we are dotting these two vectors. Good. Now the I and k component. The I and k component are 0 over here, so that is going to give us 0. So you're going to be left with only the j component. So the j component will now be equal to 2z minus 1. 2z minus 1. So our double integral over that dA. So double integral over this, then dA. Good. Now this will now be equal to this will now be, you see, we have expressed z in terms of x and y. So you have to substitute this expression in terms of z. So you're going to get double integral over d, then we have 2 into bracket 1 minus x minus y, then minus 1 dA. So now if that is the case, then we are going to multiply out the bracket. So this will give us 2 minus 2x minus 2y, then double integral over the region d, then minus 1 dA. Now this will simplify to double integral over the region d, then we have 1 minus 2x minus 2y dA. Now you can either express it as dx dy or dy dx, depending on your orientation that you have chosen. So I am choosing my line to be parallel to the x, so it means my dx has to come first. The dx has to come first. So we have double integral over 1 minus 2x minus 2y. So I'm bringing my dx first, then dy. So my boundary for y will be the lowest and highest value of y. Now for the x, I just have to express this in terms of x, in terms of y. So we have x is equal to 1 minus y over here. So if x is equal to 1 minus y, then my boundary over here will become from 0 to 1 minus y. Now we evaluate this double integral, and we are going to have our first evaluation. We are going to get with respect to x, we are going to get x minus x squared minus x squared and minus 2xy minus 2xy. Then we are evaluating from x equals 0 to x equal 1 minus y dy. So now let's from 0 to 1, 0 to 1. Good. Now what we can do now is to simplify this. Simplify this. So substitute 1 minus y wherever we see x. So I factorize x out. So 1 minus y out. 1 minus y out. Then I have 1 minus into bracket 1 minus y. 1 minus y minus 2y. Good. So if this happens, I get my dy here. If I substitute the 0, it will go. So we are going to get 0. This is 0 to 1. This is 0 to 1. So we are going to get over here. We are going to get from 0 to 1. Then we have 1 minus y. 1 minus y into 1 minus 1 plus y minus 2y minus 2y dy. So this will simplify to give us from 0 to 1. Then we have 1 minus y into this will give us negative y. Good. So dy. Now this will give us is going to give us from 0 to 1. Then we have y squared minus y squared minus y dy. Now if we should evaluate this, we're going to get y to the power 3 over 3 minus y squared over 2, and this is going to give us, so from 0 to 1, and this is going to give us negative 1.6. Good. So we have gotten this answer for our theorem, our Stoke's theorem, of our function given to us. Now another way to do is to evaluate just the left hand side. So let's do that and see whether we'll get the same result. So now this is what we're going to do. Let me sketch again. We have this to be our function. So this was our region of integration. Then it's our C1, then this was our C2, then this was our C3. Then the equation of this line is, we have this one, we have z plus y is equal to 1, and we have this one is supposed to be z x plus y, x plus y is equal to 1. Then over here we have x plus z is equal to 1. So we are evaluating on this first, but the function given to us is integral of f dot dr. This is the same as evaluating over a closed curve. So this is the same as evaluating over a closed curve of f the f given to us is z squared z squared I n plus y squared j then we have plus xk. Good. So this one, the dr is, we have the xi plus the xj then plus the y, it's not the xj, it's the yj, then plus the yj, so like this, plus the yj then plus the zk. Good. So we are dotting these two expressions. If we dot that, we are going to get integral on z squared dx plus y squared dy then plus x z. And when this happens, we are going to get now let's take this first. We are evaluating on x plus y equal 1. So we can either express everything in terms of x. So we know that x is changing from 1 to 0 over here, 1 to 0. Then y is changing from 0 to 1. So I'm going to express everything in terms of x. So y is equal to 1 minus x. Good. So whenever I see y, I put 1 minus x. Now here on this curve, which is c1, we have the equation y is equal to now all are the c's, these are all c's. Then y is equal to 1 minus x, y minus x. Our dy is equal to negative dx. Then our z equals 0, so we are going to get our dz to be equal to 0. Now we substitute everything to this line integral, and this is what you're going to have. So we have integral from 0, the x is changing from 1 to 0, then we have z squared, z is 0, so this place becomes 0, so we have 0 dx, then we also have y squared, so y as 1 minus x all squared. Then this will give us our dz equals 0, so plus x then times 0. So we are going to get, this is going to give us integral from 1 to 0, then we have 1 minus 2. I think this is going to give us minus, the dy is minus dx, so minus dx is here, so 1, so we have negative here, so negative 1 minus 2x plus x squared, then we have the dx over there. So it's going to give us minus 1, so 0 to 1 to 0. I'm actually changing this to positive, then I'll reverse the integration from 0 to 1 now. So now this is maintained, so 1 minus 2x then plus x squared dx. Now I've reversed the limits of integration, so it's the negative of it. The negative has taken care of the negative that is multiplying the whole thing. So now we are going to get x minus x squared, x minus x squared, then plus x cubed over 3 from 0 to 1, and this is going to give us 1 minus 1 plus 1 over 3. So we are going to get 1 over 3 for this. Now we evaluate on C2. Y is going to vary from 1 to 0, and Z is going to vary from 0 to 1. So I'm going to express everything in terms of Z this time. So my Z will be equal to my Y is equal to 1 minus Z. My Y is equal to 1 minus Z. So on C2 we have Y is equal to 1 minus Z. 1 minus Z. So my dy is equal to minus dz. Now if that is the case, then our z is changing, but our x is not changing. So we have x equals 0 over there. X equals 0, and our z is changing from 0 to 1. So if that is the case, then we are going to have this. We're going to have this line integral of 0 to 1. That is our C2, 0 to 1. Wherever we see z squared, we put z is maintained. So we have z squared, because we are expressing everything in terms of z. Then our dx is 0. Dx is equal to 0. So this will become 0. Then plus y squared. Y is 1 minus z. 1 minus z all squared. 1 minus z all squared. Then dy is minus dz. So minus dz. Then plus we have x equals 0, so plus 0, everything will go left with this. We are going to get from 0 to 1 of 1 minus z, 1 minus z all squared, and minus dz. This time is from 0 to 1, so we are not going to revert the sign. And we did the same thing, and we did the same thing for this, and we had 1 over 3. So this is going to give us negative 1 over 3. You can verify that. Then now let us do our last integral on C3. So on C3 I can express everything in terms of x, because I know x is changing from 0 to 1. X is changing from 0 to 1. So my z is equal to 1 minus x. Z is equal to 1 minus x. So the z is equal to minus the x minus the x. Then y is not changing. Y is equal to 0. So this will give us our dy to be also equal to 0. So let's substitute everything into the expression. We have from 0 to 1 of y squared, z squared, then z squared here, z squared dx, dx, dy equal negative dx. So we are expressing it in terms of good. So this has to become 1 minus z all squared. So this has become 1 minus x all squared. 1 minus l squared. So if that is the case, then we have our dx over here. So the x, nothing changes. Then we have plus y squared, y equals 0, so we have 0 here. Then the y is also equal to 0. So then we have the last part plus x. So x dx and x dz. But dz is negative dx. So negative dx. Good. Now let's multiply out everything. We get from 0 to 1 of 1 minus 2x plus x squared. Good. So that is the case. We have plus minus x dx. So this is going to give us 0 to 1 of 1 minus 3x plus x squared. So now differentiate or integrating with respect to x, we're going to get x minus 3 over 2x squared plus s cubed over 3 from 0 to 1.